It is a review for Chapter 8, Techniques of Integration. In Chapter 8, we learned the various integration techniques. Here we'll review 4 major integration techniques: integration by parts, trigonometric substitutions, partial fractions, and improper integrals. Here we'll begin with section 8.2, integration by parts. Okay, that formula can be obtained from the product rule. U V here derivative is same as U derivative V plus U V derivative. Now we are moving this one to the other side. Then okay, this one can be moved to the other side, so that U V prime equal, okay, that is moved here. So the UV now prime minus U prime V. So if we take integration, then it will give this one, and the second term is here, and for that is the final one. That is integration by parts. An alternative form is given in this way. Now, rather than V prime, we are using V. Then V1 is the antiderivative of V with the constant 0. Then here, okay, UV1 minus U prime V1. Okay, if this integration by parts is applied recursively, then we can get the so-called tabular method or the tic-tac-toe method. Let Vk plus 1 be the antiderivative of Vk with the integration constant 0. Then here, okay, for this first one is coming from that one. Now we have this one. And for this term, now we can do one more time the integration by parts. So the integration of that one is now V2. Now derivative of this one is U double prime. So that we can rewrite here. And then for this term, again, we can get the integration by parts in this way. So we do continuously in this way, so that somewhere now it is a repeating, or now a polynomial case, if you try to make many derivatives, then it will become 0 later on. Okay, so it is useful for those functions. Here, and the sign is a minus, plus, minus, plus. And for U derivatives, it looks like it is used in this form: minus 1 to the k, U kth derivative. Now, there is no derivative, which means a 0th derivative, so that is positive. First derivative is negative, double prime, positive, triple prime, now negative, and fourth order derivative, now it is along with a positive. Okay, so you can use this formula for repeating or some polynomials and those functions. Okay, let's try to evaluate these integrals. Okay, for this one, now this is easily integrable, this portion, and this is not easy to integrate, but differentiation is easy. So that, okay, for that one, we choose this portion as V prime, and that is now U. Then from here, V is half now x squared. So that the given integral is same as UV, okay, half x squared and logarithm of x that squared and minus integral now v and u prime. So v is half squared and that is now derivative is 2 logarithm x and 1 over x. Right? Okay, so we have that. Now, if we rewrite here, simplify, then that one same, and half and 2 will cancel out, and also for this one we have minus, and we have x here, and the logarithm of x, now dx, right? Now, for this one, we can apply one more time integration by parts. So therefore, that one here, okay. Now, that is integrable easily. So that is half x squared and logarithm x and minus integral, okay, now here half x squared, and then derivative for that term is 1 over x. Okay, so that we can get here, this one is now half x squared logarithm x, and then this is half x, so that is okay, not positive, it must be negative, and this half x, so that quarter x squared and plus c, so that we can write down the final answer in this way, half x squared and logarithm of x squared, and along with that one minus now half x squared logarithm x and minus 1/4 x squared and plus c, right? That's the final answer. Now for cosine square root of x, and because of that half power, we don't have any elementary derivative for that one, so that we may use change of variable u substitution. Okay, u is now square root of x, and then we square, so that x equal u squared. From this one, now dx is the same as 2u du, right? So the given integral is handed into now square root of x is u, so that is cosine u, and then now okay, that's cosine u, and dx is 2 du, okay, 2 u du. So 2 is coming out, and then that is u cosine u and du, right? Again, we can apply integration by parts, but even simple, we'll try to use tic-tac-toe technique for that portion. Okay, here we have here u, and now cosine u. This column, we try to make a derivative, so that it's 1 and 0. And this column, we try to get integration, so that now there is a sine of u, and its antiderivative is now minus cosine of u. So this multiplication and that multiplication is 0, so that we don't have to go further. So that is now plus, and that is along with a negative sign, so that here, okay, from this one, so the 2 is there, and then this portion is u times sine u. Okay, and that is again minus minus, so that plus cosine u. Okay, that is plus c. Now u is square root of x. This u, if this u are changed by square root of x, then that will be the final answer. Okay. Find the area of the region bounded by the curve y equal square root of x logarithm x and the x-axis from axis 1 to 4. So it is asking to find the integral, okay, from 1 to 4 and square root of x and logarithm of x and dx. That's what the problem is asking. Okay, so also for that one, here, rather than square root of x, probably you may introduce new variable u substitution, which is now square root of x. Okay, let's rewrite again. U equal square root of x. And then here, now x is u squared. And from this one, dx is the same as 2u du. Right? Okay, also, right now, x is moving from 1 to 4. X is now from 1 to 4. That means here u is moving, okay, square root of x, so 1 to 2, right? So the given integral is same as from 1 to 2, and square root of x is u, and now x is u squared, so the logarithm u squared, here 2 can go out, and then logarithm u, and dx is the same as here 2u du. Right? Okay, so here we have now there's, okay, let's rewrite here. So that 4 can go out, and from 1 to 2, and that is same as here, okay, u squared, and then logarithm u and du. Right? By using, again, integration by part, you can get the answer. Okay, from now on, you can do, you can finish it yourself. Okay. Okay, here is a special case. Once you try to get integral of inverse of functions, then now for that, you can use here for the given function, you may use y substitution, y equal f inverse of x, which is same as x equal f of y, so that dx is same as f prime y dy. So here, f inverse of x is y, and dx is the same as f prime dy. Now, we can use integration by parts. Okay, integration of f prime is f of y, and y f of y minus differentiation of y is 1. So here we rewrite here, f of y is same as x, y is f inverse of x. And now after getting this integration, y must be replaced by f inverse of x. Here we have a formula summarized. F inverse of x dx is same as x f inverse of x minus f of y dy. Okay, let's try to evaluate this integral. Now here, okay, we introduce y equal here sine inverse arc sine of x, right? Okay, and so that x is the same as sine of y. Okay, now if we are using this formula, okay, there's f inverse. So from here now, x is sine y. There's f of y, right? Okay. Now, given integral, if we are using the formula over there, then there's x times here f inverse of x, sine inverse, arc sine of x, minus integral fy is sine y, and dy, right? Okay, for this one, now we have same here, and antiderivative of sine y is minus cosine y. So along with this negation, we have a cosine of y and plus c. So that y must be replaced by here sine, arcsine of x. Okay, so that here x arcsine of x plus cosine, and here arcsine of x and plus c. Okay, that's the final answer. And for this one, you can do it by using integration by parts. You can finish the computation quite easily, or you may think of this one as inverse of e to the x, so that now, and for that antiderivative, you may write down in this way. Okay, if we are considering now only the indefinite integral, then there is x times the function itself, okay, logarithm x, minus integral, okay, fy is e to the y and dy, right? Okay, so that here we have that same as x logarithm of x and minus e to the y, and here from here x logarithm x, and here y is now okay here now e to the y, but y is that is logarithm x, so e to the logarithm x is x now, right? That's the antiderivative. You can evaluate here from 1 to e. Okay, so that you can get the answer. Yeah, now we'll go to section 8.4, trigonometric substitutions. Once integrand involves these radicals, a squared, a constant, and x squared, we can have addition, we can have subtraction, and the other way is subtraction. There are 3 cases. For the first one, x can be an arbitrary real number. There's no limitation for x value. And so that we can use tangent theta for x. Now, here, after substitution, we want to get benefit, so that we multiply a. If it is a tangent theta, then that will become, now inside the radical, a squared times 1 plus tangent theta, tangent squared theta, but that one can be changed into sec squared theta. So everything is squared inside the radical, so that we can eliminate that radical quite easily. Okay, for this one, now x cannot be larger than a in modulus, so that must be limited and small, so that we may try to choose sine theta, and because that's between minus 1 to 1, with a multiplication, this whole thing is between minus a to a, so that inside radical will not become negative. And along with the substitution, now we'll use this identity to eliminate the radical. And for that one, now x must be here larger than a in modulus, larger than a or smaller than minus a. The choice of here substitution is a sec theta, because sec theta is always larger than 1 in modulus. Okay. Now, once we are using this one, change it along with that, then later on we'll use that identity so that we can eliminate the radical. And when we try to reverse the substitution, then here we have to use these reference triangles. Okay, we'll see practically the problems, but before that, now that this case here, x is a sec theta, So then there's a sec theta, then x squared minus a squared can be given in this way. That is now a squared sec squared minus 1. That is same as tangent squared theta. So that the radical can be eliminated depending on where the value of x, what the value of x, and we can choose, and because there is square root of something squared, and we can choose positive or negative. Right? Okay, here we'll try to solve this problem. Okay, evaluate the integrals. For this one, x can be any number. It can be very large. Now, for this one, so that x, we try to use x equal 2 tangent theta. Right? X can be arbitrary number. So therefore, that one, of course, here x is between 0 and 2, but along with that change, we can eliminate this square root portion. Okay, now x is, now a is 2, so 2 tangent theta. Right? Then, now from this one, we have dx, same as 2 sec squared theta, d theta. And for this bottom, okay, x squared plus 4, that 3 over 2 is same as, now for this one, 4, okay, now that is, okay, 4 and tangent squared theta plus 4 and power 3 over 2. Okay, now 4 is there, and then tangent squared plus 1 is the same as sec squared. Okay, and 3 over 2. So that is same as 8 for the constant, and now there is sec cubed theta. Okay. Now here for lower bound and upper bound, x is moving here 0 to 2, then theta. How about theta? Once 0, then theta must be 0. Right? Now here, and once x is equal to 2, that means the tangent theta is 1. Now that must be here pi over 4. So we have here for given integral, we have from 0 to pi over 4 integration. Top is x squared. That is now 4 tangent squared theta. And bottom, we already got here 8 times now sec cubed theta. Right? Okay, and then here we have dx. Okay, dx is 2 sec squared theta. 2 sec squared theta d theta. Okay, so for coefficients, we cancel out that, and then now here sec squared theta and here sec squared theta. So we have here tangent squared theta and sec theta. Sec theta is 1 over cosine theta. So that from this one now, from 0 to pi over 4, and tangent is sine over cosine. So we have, that is a sine squared theta, and here bottom cosine squared theta, but the sec theta is 1 over cosine theta. So we have now cosine theta d theta. Right? Okay. So here sine and cosine combination. So let's try change this on the top. Sine squared theta is the same as this portion. Okay, top numerator. Oops. Okay, I made it really occurred circle. Okay, now that is same as 1 minus cosine squared theta, right? Okay, so and if we separate out 1 over cosine theta from 0 to pi over 4, 1 over cosine theta is sec theta, and then minus cosine squared over cosine, that is cosine theta, this theta. Now here, sec theta, antiderivative of sec theta is given here now, logarithm, and sec theta plus tangent theta. Okay, and then antiderivative of that is now sine theta, so that minus sine theta, we are evaluating from 0 to pi over 4. Then you will get the final answer. Okay. Let's go to this one. Now, for that one, here, x squared cannot be larger than 1. So here, we are choosing x equal, now sine theta. Then dx equals same as cosine theta and d theta. Right? Okay. And then now x is moving from 0 to here square root of 3 over 2. Then theta must be 0 to here. Okay, that is 0 to, okay, that is now sine theta is square root of 3 over 2, which is now theta is pi over 3. Right? Okay. So here, the given integral is changed into from 0 to pi over 3, and top is sine cubed theta, and bottom, okay, 1 minus sine squared theta is cosine squared theta, so that we have cosine fifth power of theta. And then here we have now cosine theta d theta. One is cancelled out. We have now fourth one, so that from this one we can write here from 0 to pi over 3. The third power is making tangent here now third power theta, and one cosine cancel out, one cosine remained. One of cosine is now sec theta. Okay. Okay, that is requiring now trigonometric manipulation. Okay, here now, okay, that one is tangent squared theta and tangent sec. Okay, so that here from 0 to pi over 3, and tangent squared can be written now sec squared theta minus 1, and then the remaining part is tangent to theta and sec theta d theta, right? Okay, for the first portion, sec squared, and that is derivative of sec. Derivative of sec is sec and tangent, so that, okay, from this first portion, we'll have 1/3 of sec cubed theta. For the second one, for second part, okay, that is derivative of sec theta, so that we have sec theta, and from 0 to pi over 3. Okay, so you can evaluate to get the value here. Okay. Okay, we have now integration of rational functions by partial fractions. So that is, we are now considering method of partial fractions. When f of g is proper, that means the degree of f is lower than g. And in this case, we can use that. And if g has a linear factor, and then it is given here up to nth power, then for this one, we have to expand in this way. Now, a constant over x minus r, and another constant over x minus r squared up to mth power, but always on the top, you have to have a constant. If a quadratic factor has power n for g, then here again you have to expand here for the quadratic factor, and top is now linear, and square and again linear, top up to nth power, but yet the top is again linear. In this way, you can expand and you can combine all the partial fractions and decide the coefficients. Here we introduce the coefficients, and then here now part by part you can integrate. Okay. Now if it is not proper, then here that means that the power, the degree of f is either same or larger than g. Then you can make division, and here that is a polynomial, and now the remainder has lower order than g. Then for this one you can apply the method of partial fractions, and for this portion integration is quite easy, right? Okay, let's try to evaluate the integrals. Okay, for this one, now it's proper, integration is proper, this is third order, and that is now a first order. So that here, but a linear and a third power, so that the integrand itself can be written in this way. Now a, the constant over x plus 1 plus b over x plus 1, here that squared, and plus now c over x plus 1 cubed. And we have to decide ABC. How? Just now try this common bottom, which is the same as now x plus 1 cubed, right? Common denominator. And for this one, now 8 times x plus 1 squared. That is b times x plus 1. And we have a c here now. So that the same bottom, now on the top, here x squared has coefficient now a, x squared. For the coefficients of x, from this one, now 2a will come out, and from this one we have a b and x. Now the coefficients for the constant term, we have here now a, and then from this one now is a b, and from the last one we have a c, like that. So here this must be same as that term. That means that for quadratic term, the coefficients must be 0. Now for this one, and 2a plus b must be 1, and then the constant term, a plus b plus c, must be minus 1. So a is 0, and then now b must be 1, a is 0, b must, okay. So here, from this one, b is 1. Now from this one, a is 0, b is 1, then c must be minus 2. So we decided everything here. That is, you don't have to worry about that one. It's 0. And now b is 1. But you can find the antiderivative of that one quite easily, right? That is, okay, along with that b, and minus of 1 over x plus 1, right? And also for this one, you can find antiderivative quite easily. Okay. Here, for this one, now we have one linear term and one quadratic term. So that you may start with in this way. The integrand is now a over x minus 1. For the linear term, your numerator must be a constant. For quadratic term, must be linear. So that now bx plus c over x squared plus 9. Exactly the same way, you try to combine them along with the common denominator, and you can decide A, B, C. Then once they are decided, then for that one, you will get logarithm of x minus 1 with that coefficient. Now, so for this one, you can separate out. You can do that integration, and also it will make a logarithm x squared plus 9 and along with a coefficient. And for this portion, now along with change variable, it is related with arctangent, right? So you can get antiderivative for these things quite easily. Okay, here. Now for this one, and also you can do it. Now here, because it's the quadratic second power, so that ax plus b over now x squared plus 1 and plus cx plus d over x plus 1 all things squared. And you have to decide a, b, c, d for quotient. Then after that, you can get antiderivative. Okay, so you can do it. Now let's go to this one. For this one, now it's okay. If you try to do integral, then it's not easy to do it directly, so that we may have to use a substitution. So as given in this hint, okay, u is now square root of x plus 1. We are making this u substitution. Then from this one, u squared equal x plus 1. So that here now, okay, now x is u squared minus 1. Of course here, dx is same as 2u du, right? So we got everything. So the given integral is same as, okay, top is same as u, and bottom is now x is u squared minus 1, right? And then here, dx is 2u du. So we have, that is, okay, u squared minus 1, and here 2u squared, and that is du. These two can go out. And here, okay, we consider here now, for u squared, you can do division practically, but now rather than doing the complication, we are trying to minus 1 and plus 1. Then this portion will make 1 here, and we have remainder part. So that they're same as 2 and integral, and that'll make 1 and plus 1 over u squared minus 1, right? Okay, du. Now, for that one, antiderivative is u, and for this portion, okay, by using partial fraction, you can do that. That one must be here minus 1/2. Okay, that is now u plus 1 and plus 1/2 over u minus 1. Okay. You can do it quite easily. Yep, yeah, that is correct. And now we have separated terms so that for each one you can get antiderivative quite easily, right? And you can see here now the answer, and try to do yourself and try to match with the answer here. Okay, now I'll stop here and I'll continue in the second part for improper integrals. Thank you.